Well, we've reached the last part of Module 3 for security practices, and this is about cryptography. So let's start by watching the video about cryptography.
Hello everyone, we are here to secure our communications. What that means, our organizations need to provide security for data that is stored on our machines as well as moving across network links. Well, to get started, we're not just going to start sending data around. Let's start first by making sure our data is the correct data. For example, on my desktop I have this folder titled Important. And in this Important folder, I've got these 6 files. Now, how do I make sure these 6 files that have data inside them have not been maliciously altered or changed since I last used them? Well, that's called hashing. It's part of data integrity. What I can do is open up another program, for example, this one, Quick Hash, and I can go to that directory, and I can select the directory of Important where all those files are in. If I go into Important and click Select, this program is going to hash all of those files. And due to the exact bits of data in each file, we will get a specific hash value that correlates to that file. But what would it look like when those files have been altered? How could I check that? For example, maybe financial records or employee passwords. Is I can go to an individual file and select it in this hash program. And how about we do employee passwords? And it will give me a hash output. Now what I can do is I can go into this file of employee passwords and I'll change it by 1 character. To change it by 1 character in employee passwords, how about dragon 0 becomes dragon 00 with 2 zeros. What I'll do is save the file employee passwords. We're going to go back into that hashing program and we're going to take a look at how this hash is about to change. Before it was 65 in the beginning, 463 at the end. Let's go to that employee passwords file one more time. Take a look at this. It is completely different. And to compare it, I'm going to paste in here what I expected the hash to be. What it should have been if it didn't change. And the program says this does not match their previous hash. If you compare those two, they are completely different just by adding on an extra 0. So this is data integrity using hashing. What we're going to look at now next is the idea of encryption. Now, what we want to verify here is that when we move our files from one place to another, it's nice to know that they haven't been modified using integrity and hashing. But it's also nice to know that they haven't been intercepted and viewed. So we need to encrypt these files. Now to do this, I'm going to use an open source program known as 7-zip. And with 7-zip, I have it looking at that directory marked as important. And I will take a couple files. How about employee passwords and employee records? I'll take these two, I'm going to right click on them, and I'm going to put them in an archive with 7-zip. And this is going to give me some options. The options first is to name the file. And I'm just going to name this file as secure.7zip. And for the password, which is going to be a symmetric encryption password, I'm going to use super secure. And this is going to encrypt these files inside of this new file known as secure.7z. And in order for people to decrypt and view these files, they'll have to have the encryption password of super secure. Since it's the same password used to encrypt and decrypt, that's known as symmetric encryption. I'll click OK, and we're going to encrypt those 2 files. First one's done, and second one's done. So I've got this new file, secure.7z. In order to gain access to it and view the confidential data inside of it, I have to right-click, go to 7-zip, and I'd say extract to secure. From there, I get my password pop-up in order to decrypt the contents, and that would be the password again of super secure. You can see it, and I'll click OK. From there, it's going to open up a new directory right here. It's decrypted those files, and now those files are right here. If I wanted to now, I can verify these files have not been altered in transit, and that would be by using my hashing program for data integrity. So cryptography here is going to provide you data integrity, origin authentication, making sure a message is not a forgery, and actually comes who it said it came from, data confidentiality, which is our encryption, and making sure that data is intercepted, it can't be deciphered, and also non-repudiation, where it guarantees that the sender cannot refute the validity of their message. They are the one who originally sent it, and they have signed off on it.
Okay, so we're going to see if we can finish out some of this cryptography. section of this module. And again, here's just a nice picture of showing all of the different types of where you would want to put security and where cryptography may come into play, right? Because cryptography is something that you would do in addition to the mechanisms and software and different technologies that we've already talked about. So if we break down what the video went over, which I thought, again, that did a really good job of a high-level overview of cryptography, data integrity being the first one. So there's a couple of different types of hash functions. We've got the MD5, SHA-1, and SHA-2. Basically, you'll always want to use SHA-2, and you will still want to use that with additional types of cryptography and different mechanisms to protect your data. So hash functions ensure the integrity. So it ensures that what you start with at the source is what you end up with at the destination. And so basically the sending device will input a message into a hashing algorithm, and it computes the length, okay, of that. So everything goes over in plain text, which is one of the reasons that hashing is no longer considered secure enough. Now, the receiving device will remove the hash, and then it's essentially comparing the length, right? So if the computed hash is equal to the one that is attached to the message, then the receiving end knows that it wasn't altered during transit. Now, there is still a way to remove the existing hash, put a new hash on that is through a threat actor. And so that would be a problem because at the receiving end, they would have no way of knowing. Okay, so again, we've got the MD5, the SHA, and the SHA-2. So here's, again, why we want to point out that hashing with MD5, SHA, and SHA-2, it's not necessarily the best way, and so you don't want to rely on this. And that is because hashing will detect accidental changes, but it cannot be used against deliberate change. So again, I, as a threat actor, could get a hold of the data and remove the existing hash and put my own hash on it, right? So that's what makes hashing vulnerable. Origin authentication, right? So this is when we add another layer to our hash. We have something that's hashed, but then we're going to add a security key, right? So we add authentication to the integrity assurance using a keyed hash. So I'm still hashing, but I'm adding a key. HMAC is calculated using any cryptographic algorithm that combines a cryptographic hash. So again, we can use MD5, SHA, SHA-2, and then we include the secret key. So only parties who have access to the secret key can compute the digest of an HMAC function. So this at least eliminates the man-in-the-middle attack. Okay. And then we've got data confidentiality. So there's two classes of encryption used to provide data confidentiality. It's DES and AES. Now there's a couple different types of DES, 3 DES being the currently accepted form of DES. Let's see, data confidentiality can be ensured using asymmetric algorithms or symmetric algorithms. The figure highlights some differences between each encryption algorithm method. So symmetrical, we're using the same key to encrypt and to decrypt, and this is a faster form of encryption and de-encryption, okay? And it will use less of your resources. It's common for VPN traffic. VPNs are very data and resource intensive, so sometimes it's better to use symmetric encryption because, again, you're already on using a protocol or using a technology that's very resource intensive. Asymmetric, we're going to be using a different key to encrypt and decrypt. So on each end, the sending and the receiving, we're using one key to encrypt and another to decrypt. Also notice here you can have a longer key length, which of course means it's going to be slower because it's more resource intensive because it's having to decrypt this longer hash, 4096 bits versus the most for symmetrical would be 256. So let's see, commonly used for quick data transactions such as HTTPS. So this is something that when you're accessing your bank, really anything where you're using a password and a username, it's probably using this type of asymmetrical encryption. All right, so again, just a breakdown. For integrity, we can use MD5 and SHA. For authentication, HMAC combined with MD5, HMAC combined with SHA, RSA and DSA. For confidentiality, we're using DES, not so much anymore, 3DES or AES, the asymmetrical. Okay, so symmetric versus asymmetric. Basically, again, source, destination, you've got the same thing for encryption and decryption. Whereas for asymmetric, we've got an encryption key that has one set of parameters and configuration codes versus on the other end, for the decryption, we are going to have a different set of values. So symmetric algorithms use the same pre-shared key for encryption and decryption. We've already stated that. It's less CPU intensive. And you want to use a minimum of 128 bits, but it can go as high as 256. Now with asymmetric, it starts at 512 and it can go up to 4096. Right here, again, if you're going to be using DES, let's make sure you're using 3DES, right, the newer version. And then advanced encryption standard. This is actually even preferred, right? Because AES is secure and more efficient than 3DES. It's got more bits, plus, even though it is resource intensive, it's quite fast. And then we've got SEAL, software optimized encryption algorithm. SEAL is a faster alternative to symmetric encryption versus DES and AES. And Rivas ciphers. I don't think this chapter goes really into in-depth for ciphers. If it does, we'll cover that a little bit more as well. Asymmetric algorithms are known as public algorithms. We've seen these before, right? We're using a public key and a private key. Because neither party has the shared secret, you're going to have very long key lengths must be used. Examples of asymmetric would be IKE, secure socket layer, SSL. So this we've seen a lot. Of course, we're familiar with SSH and PGP. This computer program provides cryptographic privacy and authentication. It is often used to increase the security of email communications. So, you know, I'm not really great with all of this security stuff, but one of the ways I remember pretty good privacy, PGP, is I think of POP, P-O-P, like POP mail. Asymmetric algorithms are slower. We've already talked about that because they're really resource intensive. However, they're much more secure. Different asymmetric encryption is going to use different types of encryption mechanisms and algorithms. So the Diffie-Hellman, that's one that we've heard of before. DSS, DSA, RSA, EI-Gamma, and the elliptical curve techniques. Diffie-Hellman is an asymmetrical mathematical algorithm where two computers generate an identical shared secret key. However, they've never communicated before. Again, super resource intensive, so you're not going to see Diffie-Hellman used on very many things. If you have a lot of data, you're going to back down to the 3DES or AES.